Okay, so what we're going to be doing is a demo, but we have to do a lot of setup for that. We are demonstrating at-scale monitoring of OpenStack Cloud using Prometheus. We put in that Prometheus keyword because that's popular these days. We had a talk in Berlin as well where we explained why the current OpenStack monitoring was not scaling. So if you want to take a look at that, that'd be good. We just start reporting what we've done since then. Right. All right, I am Anandeep Panu. I am a product manager in the cloud platform organization within Red Hat. And this is Pradeep Kalambi, and he is an engineering manager in the OpenStack engineering team. And we'll go on to the first slide, which is the agenda. What we wanted to do, which is normally not done in open source conferences, is actually talk some strategy, right? And talk about a vision for what we want to do with day two operations and monitoring specifically. And then what critical features we believe we need for monitoring clouds. We have something we call the Service Assurance Framework. It's a framework that we have developed for monitoring clouds, starting specifically with OpenStack. But our hope is that, given the name of this Open Infrastructure Conference, it is able to monitor all infrastructure using the same approach. We'll talk about the evolution of the Service Assurance Framework. Pradeep will go over the deployment and configuration with some actual code and stuff. And then we'll go through a short demo, given that we have a lot packed in here, showing you some of the capabilities of what we have developed. So on to the next slide. Definitions. So I've thrown out day two operational management as something that people talk about. What does it mean? I think this is from ITIL. It's a definition of what day zero, day one, day two, and end state of a cloud is. So day zero is requirements, architecture, and design, where you are talking with your customers or your partners on how to set up a cloud. Day one is installation, and in the case of Red Hat OpenStack, that is done using the director component. Day two is what is lights on maintenance, housekeeping, and optimization of the cloud. This is the longest living piece of the life cycle of a cloud. And that's what we are focusing on now. And of course, the end state is when you delete and clean up. I just wanted to, this is from one of our documents that talks about, hey, here's what we're doing for day two. It includes the following tasks: environment maintenance, health maintenance. Health, is everything healthy? Are the services running? Hardware is good. Doing capacity expansion or the reverse, bringing down capacity. Updates, security updates, or optimization or feature updates that happen to the software that runs the cloud. Backup and restore at the host level, storage, project, tenant level. That is also part of day two operations. And then, how we make money is billing. That is also billing, chargeback, that kind of stuff. Notice that upgrades are not considered day two operations, since they require, in most situations, when you upgrade from one major version to another, you are reevaluating your day zero requirements, and then you have to re-provision sometimes. So that's why they're not considered part of day two operations. One thing that day two cloud operation management does not mention, but is absolutely critical, is that metrics, monitoring, events, logging. You heard of that. That's what monitoring is about. But these are not mentioned implicit. They are implicit in day two cloud operation management capabilities, because they are the infrastructure capabilities that enable those day two use cases. So when we talk about monitoring, it is part of the day two stuff, but it doesn't appear in the definition. So now let's switch gears, and this is the strategy part of the talk that what is required to do cloud monitoring, right? For open infrastructure, what would be the kind of things that we should think about? First, and these are assertions, and you can call them my assertions or Pradeep's assertions, but what we believe is going to happen is that Day 2 operational management capabilities will be critical to the open hybrid cloud, whether it's OpenStack, and we are specifically focusing on OpenStack monitoring today, but when you talk about the complete stack, be it Kubernetes or other applications running, you need those operational management capabilities for the entire stack because our customers expect public cloud reliability, and the same stuff that they're seeing running on their on-premise will be running on public cloud, and they want to see that it's running the same way. It's easy to update. If something goes wrong, that it's now a comparison, right? And then the costs of maintenance also are expected to be comparable. Part of what we are finding is there used to be a complaint that OpenStack was hard to deploy. We worked to solve that. Now they're saying OpenStack is hard to manage. So that is another issue that we will need to address. The second assertion I say is that operational management capabilities will be portable across all footprints. They don't want to operationally manage Amazon or Google or Microsoft running their Kubernetes application, say, and their on-premise management being different. You want to take that operational management you're doing and migrate it to this other cloud and use the same across all the footprints that you're going to be deploying cloud on. The other thing that we'll find is if you've got bare metal, you've got a data center, you need the capability to monitor hardware, right? Not so much in AWS. So what this third assertion says in many more words is that you need capabilities that are specialized and APIs that allow you to go to whichever level you need to do that monitoring, that fault management, that update, right? And it has to happen across multiple footprints, and that also says that it better be the same thing, because if you're using the same API and it applies to this second footprint, that you shouldn't have to change those. Next slide, please. So the method of delivery is also this. I've talked to a few people. They offer capabilities for operational management as a SaaS or as a managed service. I don't want that to be different from what I'm using in on-premise. I want the same method of delivery to work with that piece of software. And the final thing is, whatever we are doing as open infrastructure, if it's important, if it's edge, it doesn't work if our operational management capability does not support edge, right? So this should not have to be said, but the same priorities need to apply to operational management as applied to the actual capabilities that we are trying to address. So that then results in the critical features. Go to the next slide. That I believe these are the critical monitoring features that we will need to do. We want monitoring to be a Kubernetes application. That's because it gives us portability across different footprints, HA, scaling, persistence, all of that for free. You can reuse some of the platform capabilities that are available with Kubernetes. We need access to multi-layer APIs and multiple open source components. So users integrate, say, and we'll talk about a message bus we use shortly. If they want to use Kafka, they should be able to use Kafka. If they want to use AMQ, Cupid, they should be able to use that, right? And then stringent SLAs may be needed for some, for others not so much. So all of that, you need a multi-layer approach with pluggable components. Metrics capability in every component is now necessary because if you are collecting metrics from different components and they're different formats, they're different, and sometimes they're just opaque, you don't know what metrics they can give you, now you have a problem, right? So, and then edge use cases, I think, going across the firewall to the edge, across at least the virtual firewall, the physical firewall, that needs to be supported implicitly. It can't be a solution that, you could be running your monitoring application on AWS and monitoring something on-premise. That's a possible topology, right? Analytics, ML, they're all important. You can't, with the kind of monitoring information that you're getting, it's just impossible to have someone sitting there and looking at alerts. Right? You need some integration with analytics. So those are the critical features, I believe. I will now hand it over to my colleague to talk about the architecture we believe addresses all this.
Okay, thank you, Anandeep. So as Anandeep mentioned, based on the assertions and the critical features, we had the need to come up with an architecture that's scalable, right? We have, the amount of data that these monitoring applications gather and send and persist. We need a scalable architecture that works across board, regardless of the tooling that you use. And we should be able to do our averages, be able to look at our sample rate and gather at close to 50 millisecond sample rate, right? So with that, we came up with something called a service assurance framework, which is an integration framework with multiple components. So this is a very high-level architecture overview of how service assurance architecture runs. So service assurance framework is a microservice application, right? It runs on top of OpenShift or Kubernetes. So all of these pieces that you're seeing here have an equivalent open source tooling that you can use and be able to deploy in your data center. And then OpenShift, aka Kubernetes, needs to run on some infrastructure layer. So that infrastructure layer could be OpenStack. It could be runs on top of AWS, or it could be running on top of Rev. You just have your own bare metal RHEL nodes, run overt on top of that, or Rev on top of that, and be able to deploy, this application. So the advantage of service assurance framework is it's platform agnostic, right? You should be able to pick your infrastructure layer, pick your, so long as you have Kubernetes running on top of your infrastructure layer, you should be able to run it. So as Anandeep mentioned earlier, the need here is to be able to provide data at various access points, right? You don't necessarily need an entire framework to be able to look at your data. So when we are collecting data on the OpenStack side, we should be able to provide API access at the OpenStack level, or be able to send the data through the bus and be able to access it at the bus level, where maybe you have SAV1 integration and you just need the data and you don't really need any of the monitoring framework. Or you need the full-fledged monitoring framework to be able to do an end-to-end monitoring. And we provide all three levels of access points. So obviously you might be familiar with Telemetry, Naki. These are the telemetry, OpenStack telemetry services. They're not going anywhere. So we continue to support them, but for billing and chargeback only, because they do not provide a scalable monitoring solution and metric solution for us. So we still continue to support them, their OpenStack projects, but they are supported for very limited use cases. So here is a little more deeper view of how the data flows, right? So at the bottom is your client, aka your OpenStack nodes, your Ceph nodes. You have let's say you have three controllers, computes, and Ceph nodes. We basically run collectd, which is our tool of choice for gathering the data, which has a lot of plugin support, and we work very closely with the plugin community, our upstream community, and work with a lot of vendors to provide performance data. So you can run collectd, and then we provide this AMQ bus, which is an AMQ message interconnect, and upstream it's just an Apache Cupid router, and they have multiple modes in which the router runs. They call it the QDR, so Cupid Dispatch Router. So you can run it in edge mode if you want it to be very low key. Or you can run it in full-fledged core mode as well. So the data is put on the message bus. So we have a Proton client that basically fetches the bus data onto the bus and then grabs it off of the bus. And then on the top, this is where what you're seeing is the Prometheus operator cluster, right? So the service assurance framework server side is basically a monitoring infrastructure that is standalone from your cloud. because that's how we think monitoring infrastructure should be, right? If you're running on your cloud itself, like the legacy like for example, your Telemetry and Noki deployment runs on your controllers. So if your controllers go down, there's a chance of you losing data, or you don't have visibility of what's happening. So the advantage of keeping the monitoring infrastructure outside of your OpenStack cloud is that, anything that happens on your OpenStack cloud is preserved on your external monitoring infrastructure. And the external monitoring infrastructure has, Prometheus. We use that for metrics. We have Elasticsearch, which stores events. And there is a QD router that gathers the data from the AMQ and then puts it onto the bus. And we have third-party integrations for, as I said, Sub 1. You don't have to send the data to server side. You can directly grab the data off of the message bus, which is the red and yellow lines, which are metrics and events, and then integrate it with your third-party tooling if you want. So a little deeper view on the components that we use. So collectd, as I said, we run the collectd containers on the OpenStack nodes themselves, and we work with the upstream community. We have, they are basically the Cola containers. We have OOO integration that basically does the deployment as part of the OOO deployment for OpenStack, and we have it in production for OSP 13. And some of the code actually got released yesterday as part of our Z release as well for the QDR integration. So we support a bunch of collectd plugins. So for example, this is the latest OSP 14 version, and we added recently the Write Kafka, syslog, Prometheus, and a bunch of other plugins. And we do have support for a lot of NFV-specific plugins for some of the telco deployments as well. So the next piece of the puzzle is the AMQ interconnect, right? So this is actually the highly scalable, high available bus that gathers millions and millions of metrics. The reason why we chose this is because it has a very high throughput. This has a mesh router topology. So the way it works is you have multiple routers running on different nodes. It creates a mesh network and figures out the shortest path algorithm to send the message as quickly as possible to the server. And this has a lot of upstream community, and there is already integration into Puppet OpenStack, Puppet Ansible, Ansible OpenStack Ansible, as well as in OOO. So it just fit right into our architecture. So the last piece of the puzzle here, the main component here and the star of the architecture is Prometheus operator, to be honest. So because that is what provides us the scale at which the metrics we write. We gather millions and millions of metrics, and Prometheus does an excellent job of scaling that. And as you notice the word operator, so we actually use operator framework, which is a CoreOS-based lifecycle management of your application. So I have a little bit of a picture of how the operator framework handles the state. So basically, you have an observed state. It does a little bit of analysis, and then it acts to get you to that state. So you can create a custom resource in Kubernetes to say that I want a specific version of Prometheus, and I want to deploy it on, say, 3 pods. Right, and when there is a new update, you can update that custom resource, and when you deploy it into your Kubernetes infrastructure, it basically updates that and manages the whole life cycle of the operator. And I don't want to go deep into what Kubernetes Prometheus is and what it does. It's a very popular monitoring, open source monitoring tool, and it basically uses an HTTP scrape to basically grab the data off of the endpoints. So there are a few other pieces on the server side. So as I said, we use Elasticsearch as well. So Elasticsearch is used to store the events so we store metrics in Prometheus, we store events in Elasticsearch. We have Alert Manager, which goes hand in hand with Prometheus to define our alerts, which is the demo we will be showing in a little bit. And Smart Gateway. So Smart Gateway is essentially the brains behind the server side, right? So it does a lot of the integration work. So it takes the data in, converts that data to something Prometheus understands, and then exposes an HTTP endpoint for Prometheus to scrape that. And similarly, it does the same for events as well. And when we have once we do the alarm integration, when an alarm is triggered, it automatically sends the message back to the queue. So we have like a closed loop monitoring. So you can tell the OpenStack node that, okay, there is an alert here, and the user already knows that there is an alert. And the Grafana integration is optional, but we do provide the Grafana data source, so the Prometheus data source in Grafana to visualize the data, if you like, but that's not part of the core architecture. So with that, I'll pass it on to Anandeep to talk about the evolution of this architecture.
All right, so the first thing we encountered is, oh, you're running a separate Kubernetes cluster. It can connect by AMQP to multiple clouds. Why aren't you giving us multiple clouds? So what we are planning to do is do the topology that is demonstrated here, which is you could have a centralized Prometheus with AMQP on multiple clouds, multi-site, that can send the metrics back to this central Prometheus. We also can go federated, which means that you can have a Prometheus that's local to a site, and then that forwards that data to the central Prometheus site, so you can manage everything from that Prometheus management cluster. Prometheus being a time series database and a set of capabilities for monitoring, you're able to use all that to visualize, to do alerts, to do queries, to set up a whole set of monitoring that you want to set up. So the first use case that we are actually supporting will be the DCN, Distributed Compute Node use case, which is part of the edge strategy that we are following, where there are compute nodes that are L3 routed that are on multiple sites. We will have one single service assurance framework that will have an agent deployed, a QDR, which is a Kubernetes dispatch router, on this compute node, and that'll be transparent to Prometheus, that those nodes are also sending data, and you can monitor those as well. The final thing that we wanted to get to is what we call closed loop infrastructure monitoring, where, like I said, you can't have an operator just sitting down looking at alerts or even visualizations. What we want to do is, once we get all this data, we should analyze it, and then the remediation should be automatic, and that closes the loop in the in this whole monitoring day two operations management for cloud. You need to get that done, because given the scale of what we will be doing, this is absolutely needed. And back to you.
Yeah, cool. So with that, let's look at a little bit of code and see how we do the configuration and deployment of both the client and server, right? So client in this case is the OpenStack nodes themselves, and the server, which is a service assurance framework. So as I said, we use OO. So collectd and QDR both are containers that run on top of the control nodes. So each node is configured so that collectd basically gathers the performance metrics off of the controllers, computes and Ceph nodes and whatnot, and then sends it to the QDR. So the QDRs are then configured to talk to the central QDR. So each of these edge QDRs which run on the OpenStack nodes are configured to talk to the central QDR, and then data is being sent across. If you're familiar with OO and how the heat configuration and all that works, this is basically what we do. So you can create an environment template and enable these resources in your resource registry, right? You have the metrics QDR and collectd. So the only extra thing you will need to do is to set the collectd connection to use AMQ 1.0, right? Instead of 0.9, we use 1.0 for the throughput that we need. And then you can define, the notification mechanism, and whether you want to, what format you want to get the data and all that. And then there are a few parameters that you need to override for you to configure collectd and the metrics QDR. So we use SSL, TLS across board. So when you have TLS everywhere is enabled in your OpenStack director or OO cloud, you just need to make sure you set the SSL profile and the ports correctly, and you have the host name. just make sure the hostname is resolvable and be, that's something that can be resolved across your network. And once you have that, just pass those to your overcloud deploy, and this essentially deploys your overcloud with all your nodes configured to use collect D and QDR, and the setup is in place. Now, now that you have your client side in place, we need to configure the server side, right? The server side, as I said, is a microservices application running on top of Kubernetes. And for the infrastructure layer, we use Overt with Gluster as the storage backend. And we use the hyperconverged RHHI, aka it's called Red Hat Hyperconverged Infrastructure. The main advantage of using this is the smaller footprint, right? So all you need is the 3 extra nodes for high availability. If you don't need that, if you are restricted to one node, you can actually run this on one node as well. If you want to do a single node deployment, we support that as well. So as I said, we have the 3 core components that we need to deploy, and all of these are operator-based. So these are all, we already have these containers in Quay as well as in the Red Hat Container Registry. And we have an operator lifecycle manager that basically orchestrates the operator for each of these operators, and then does the deployment. So I'll show you how the flow happens. So this is a server-side deploy. So our code is basically in this GitHub repo. Again, it's open source. Anyone can go and play with it. So we have a deploy script, and you just do a deploy create. What this basically does is the following, right? First, it deploys the operators, right? And then it defines a few custom resources, and then make sure each of these services are configured to talk to each other to create the service assurance framework. So all of this is running on top of Kubernetes. So a little deeper into the flow, when you run the script, so what we are doing is, in this case, for example, we are creating the Prometheus operator, and you see that we create a cluster role and bindings and service account and all that, exactly how you would deploy any Kubernetes application. And then you need the AMQ interconnect operator, which is the server-side operator that takes in the data, and the smart gateway operator. Again, if you have events, you can create the Elasticsearch operator and then run it right here. And it should be the same workflow. And then in the next step, as you see, we are creating the custom resources and putting the configuration in place. And the end result, which is the service assurance framework, is you have these deployments in your Kubernetes. If you do kubectl, you should be able to see all these deployment services in place. So with that, let's jump to the demo. So our goal for this demo, and it's a short demo, but we want to make sure we convey the message with the service assurance and alerts. So what we are trying to do here is we are monitoring an OpenStack cloud. We have an OpenStack cloud running, which is OSP 13-based OpenStack cloud. We have collect D and AMQ configured. We have service assurance framework with a few alerts already pre-configured in Alert Manager. And these are the 2 alerts that we will be primarily looking at. We have other alerts, but this is what we'll be demoing. In this case, we have the CPU alerts for the load, and I'll show you that in the demo. So essentially, one is the warning. We'll monitor an OpenStack node and watch for the CPU load and trigger a warning alarm, and then we'll wait for the load to go up to the critical level. We'll show you that the critical alarm is being raised. So this is the flow of the demo. Also, it's a good recap of what we talked about so far. As you see, the OpenStack, Red Hat OpenStack platform, where you have your container images deployed on the OpenStack nodes. You have the AMQ interconnect, so collect D is gathering all the data. That data gets sent to AMQ interconnect on the server side, and the smart gateway takes care of analyzing the data and converting that to the Prometheus format and exposes a HTTP endpoint. And as you see, Prometheus operator is basically scraping the data off that endpoint, and it stores the data. And similarly, when we have alerts, the smart gateway basically pushes the alerts to Elasticsearch. And you can visualize that data through Grafana. And at the bottom, all this is running on top of RHEL, Red Hat Enterprise Linux, with RHHI, which is a hyper-converged infrastructure. So with that, so we have a pre-recorded demo. So we'll basically, I'll play the demo and I'll talk as the demo progresses here. So what you're looking here is basically the Prometheus UI, where we are showing you the alerts being configured, right? So we have the warning CPU usage and the critical CPU usage. These are the two alerts that we have configured in the alert manager. And when the service assurance framework is deployed, these are already configured and part of the containers that are being deployed. So we have the warning CPU usage, as I said. So essentially what the warning CPU usage is looking for, so this is a PromQL query, if you're familiar with PromQL. So it's looking for an average load, CPU load over time, and making sure that load is between 75 and 90. So if the load of your CPU is between 75 and 90, then for at least 10 seconds, then we would want to fire a warning alarm, right? So we don't want to fire an alarm if it is fluctuating. So if it's going back down, we are fine. Similarly, for the critical, we want to make sure it's at least 90 or above for us to be able to raise that alarm. So what you're seeing here is the Grafana dashboard. So if you see here the CPU percentage used, that's where we will notice that the load is going up. And if there are any alerts fired, you'll see that in the alert firing dashboard. So this is a simple script that we will be running on the controller nodes themselves, right? In this case, I'll show you that we are running this on the controller 2 of our OpenStack node. So what we are running is we're just running a simple stress ng. This is just putting some load on this node and making sure it reaches at least 76. The CPU load is 76 for 20 seconds, right? And once that happens, we will wait for 10 seconds for it to recover. And then we will do another stress to make sure the CPU load goes to 795. So what we will see in Grafana is the load increases on your OpenStack node, right? CollectD basically gathers this data, sends it to AMQ, and we process that in Prometheus. And basically, when the load hits 76, Alert Manager automatically triggers the alert, right? And we will see that alert being raised in Grafana. So now let me play this again. Okay, cool. So here, as we are just showing, it's the same alert that we have configured in Alert Manager, and that will be triggered when we run the script. So the script is currently running for 20 seconds. So let me move to the interesting part, so we don't need to see all this. Yeah, here. Yeah, so currently there is no data. So yeah, let's get to the no data part. Yeah, so currently there's no data. We are going to kick off the script at this point, and we will see that slowly the CPU usage in this particular window at the bottom, that will start to creep up. So as you see, yeah, there you go. So you're slowly seeing the load go up. And as we continue to see, the load keeps going up, and we wait for the recovery time of 10 seconds. So we will see the load kind of stabilize at some point, and then it'll trigger again when the 90% load kicks in. So we will see that, yeah, now here, we still don't have any alerts being fired, and there is still no data in this dashboard that we are seeing. But we should soon start to see the data. So, right, we are getting close to 75. And now in the alert firing window, we see that the alert is there, but it's still in the pending state, right? We haven't fired the alert yet. It has triggered the alert, but alert hasn't fired. Now, once we hit the 76, we are seeing the warning alert being fired. And that shows that, okay, so the CPU load is between 75 and 90. Right? And then here, when we refresh this window, we will see that the warning alert is one active alert has been fired. And in this case, we see that the load has reached above 90. So we see that the critical alert has been fired as well. So And then we'll go back here, and in the dashboard, we will see that the critical alert also has been fired. So now, when the critical alert has fired, the warning obviously goes away. We don't want to be firing both warning and the critical alert at the same time. So the warning alert will go away, and the critical alert is still firing at this point until the script will end momentarily, and then we will start to see that now that the script has ended, now the load should start to come down, and then we will see that the critical alert will move from the firing to pending state. So as soon as it reaches below 90, now it's in the pending state, and it'll keep going down. And when it hits below the 90, it gets to the warning state, but it's still in the pending state. We don't fire it at that point. And then eventually we'll see that both the alerts have gone away. So that's basically the demo. So essentially what you're seeing here is data actually flow in from the OpenStack node, Collect-D gathering the data, sending it to AMQ, and then sending it across to service assurance onto the Prometheus side, and then we do the alert manager. So we have a lot of already pre-canned alerts that we ship, but that's something that you can already configure. Yeah, and if you need to add more alerts, you should be able to do that as well.
Just to add to what Pradeep said, it's not just an alert firing. It also says that average has to be held for a 10-second period. Right?
Yes.
So you can do very sophisticated queries like that and avoid the kind of alert explosion that happens when you have them.
Okay, so finally we have some links here. So that's where our documentation is, if you're interested. The Smart Gateway operator is on Quay already, so you should be able to go and download and play with it. This is where our GitHub repo is. So we have an upstream IRC channel, service assurance, so feel free to join there, and we'll be happy to help if you want to get involved. I think with that, we have like 3 minutes for questions. So. Any questions?
What happens if Smart Gateway stops working? We have Smart Gateway replicated across the 3 nodes, and we have a load balancer that handles that.
So Smart Gateway is an operator, right? So the lifecycle management of how any Kubernetes application is handled. So if one part goes down, Kubernetes makes sure there's another part automatically coming up and make sure Smart Gateway is up. Yeah.
How do you approach the problem that the system monitors itself?
Yeah, I mean, so if you...
Let's repeat the question for the... how do you approach the problem that the system monitors itself?
Yeah.
Right, so
monitoring systems down, what can you still monitor?
Well, so monitoring system is down. So you mean to say if the server-side framework is down, how do you monitor? Is that what you're saying? I'm not getting your question.
What do you do if the platform that you are monitoring is also hosting your monitoring system?
Right. So which is exactly why our architecture keeps the monitoring infrastructure outside of the cloud that you are monitoring.
So it's a separate cluster, a separate OpenShift cluster that is running service assurance as an application.
Yeah.
So it's outside of what you're monitoring, whether it's another
your cloud
OpenShift
is
cloud or
side. So that is your infrastructure. So even if your cloud goes down, we have all the data that's preserved in the monitoring
you can go do the
infrastructure.
diagnosis.
Yeah.
Why have you decided to use Collect-D for collecting instead, for example, for scraping Prometheus endpoints directly?
Okay, so we wanted to do as a first approximation, we wanted to make sure that we were able to collect NFV infrastructure information. There's a lot of plugins that are already available, such as OVS stats, DPDK, SRIOV, those kind of monitoring that are made by Collect-D. Our architecture is such that we can put in a node exporter, for example, where we don't have to scrape. but we wanted to support both the push model that CollectD has because of the ecosystem of plugins that are built in with that, and the pull model. So this is one way for us to make the Prometheus pull model work with the CollectD push model.
And another question, how are you sharding your data? So you have separate Prometheus instances for every cluster you monitor, or how is it organized?
So currently in our first release, that's why I was talking about the evolution of multiple clouds. We are, as we shown, we have 3 instances of Prometheus that are mirrored, right? They all have the same data. That is, as when we release it now, it's in tech preview, it has only one cloud's data. But what we are working on is one of those clusters can then do multiple clouds. And what we do is we are exploring using tags to keep it in the same database, but separated by the tags from which cloud that data came from.
All right, so the current setup is just HA with 3 systems?
Yes.
Correct, yeah.
And you would like to?
Yes, absolutely, yeah. We are working on it already. Yeah.
Okay. All right, thank you.
All right, I think our time's up. Thank you very much for listening.
Thank you very much.